perspectives on where big data could be used, machine learning in particular can be used in this space, and also some challenges and potential barriers that could exist. But I'm going to turn things over to my colleague, Dr. Matukumalli, who is Vice Director, sorry, Madhu, I should know, Associate Director, sorry, of the Institute for Sustainability, Energy, and the Environment on campus, which is also a co-sponsor of today's and tomorrow's event. Madhu.
Okay. Good morning, everybody. So, as Kathy just said, I'm here to moderate this session. I'm Madhu Khanna. I'm a professor in the Department of Agriculture and Consumer Economics and an environmental economist by training. I'm also the associate director for the Institute for Sustainability, Energy, and Environment on campus that many of you may have heard of. This is a recently formed institute, and before we get started, I just want to give a 1-minute spiel on what the Institute does, since that may be relevant for this group as you're going forward in developing this area and in developing some opportunities for collaboration and fundraising. So the mission of the Institute is to support interdisciplinary research on campus, and we do that in a variety of ways. We try to do a lot of matchmaking on topics of interest, bringing people together from different disciplines so that they can collaborate. If you can go to the website sustainability.illinois.edu, and we have created networks of energy scholars and water scholars, and we are creating another one on climate scholars. So that lists the expertise available on campus on each by topic areas. You can search it, and you can get to the web pages of these individuals. So that's one way virtually that you can use the resource that we have. In addition to that, we also provide support in developing proposals. If you're developing multidisciplinary proposals, we have the capability to help. We have support staff who will do all of the administrative work for you and get the proposal submitted. So all kinds of support like that that's available. We don't take any of the indirect costs. If you're thinking about that, that goes back to the department. We're really just here to provide a service to campus by providing more opportunities and making it easier for people to collaborate and do interdisciplinary proposals. So again, happy to talk after this, and if you have ever, if you'll get to this point, have questions, feel free to email me or go to the website, and you can find our contact information there. Okay, so with that, we'll get started. We have a pretty intensive panel. We have 5 speakers, and given the time, I'm going to ask them to speak for about 10 minutes each so that there's enough time for questions and answers after that. The main idea about this session is to look at what is the current state of knowledge. What do we know about the use of machine learning as of now? How can we enhance it? What are the opportunities for collaboration? What are some of the barriers to that? And where in this broad field of agriculture, food, energy, and water, and so on. So we've got a diverse panel, and we're going to start with Tami Bond, and maybe just take a few minutes to introduce yourself and your work, and then tell us what you do.
Okay. I either need to stand up or turn my head around 180 degrees, which would be pretty ugly. So I think I'll stand. So my introduction is in here. Does that introduction come off of my 10 minutes, or is it added? So I think I'm gonna pretty much show you what I do in here, and I actually am disobeying instructions because what I do is a little bit different from a lot of people in the food space, and so I want to introduce you to the topic I work on, and then at the end I have a couple of things that I think could be important uses of data management, data mining, and machine learning, but I'm going to let your imagination run wild too. So what I do is I work on the part that farm-to-table people typically don't think of, I think, or maybe I'm totally underestimating you, forgive me if so, but when you take it from the farm and it goes to the table, most of the time you cook it and process it. And my interest over the past years has been, particularly in rural areas of developing countries, people are using energy, and so how do they get that energy? And I have been completely ignoring the food part, right? Of course they have food, but I'm worried about how they cook it. But there's obviously an enormous link there. And so a lot of people who do cooking think of actual cooking, but in addition, there's many, many opportunities to use energy and require energy within a household or a homestead. Oh, it's one of those shape things again. Okay, so this is energy in the United States. A lot of it is space heating, about half of it. And if you look for cooking, it's really tiny. It's 4%. And so we don't tend to think of cooking as a big deal. But if you were to look at Africa, it's 3/4 because they don't have the access or the resources to undertake a lot of the things that we do in our households. So when you look at cooking as a fraction of the rest of the world, or many places in the world, it's a huge piece, but that's not all there is. And if you were to squeeze that down to the US scale in terms of per capita, then it would be a much smaller slice. So you can see there's actually probably a lot of unmet demand. In Africa, fuel comes from the forest and it comes from the farm, and there's a little bit of other stuff, and it would be wonderful if there would be more, but right now it's the forest and the farm, and that means land use, and that means it's part of a managed system or an unmanaged system, but regardless, it's part of a system. So here's the old view. This is what people have been doing for the last 25 years. Here, you have a problem. You are cooking and you're doing it inefficiently, and it's causing you to die, and it's causing deforestation, so I will bring you a new cooking stove. Goodbye, I'll see you later. And so this is the new view that we're trying to promote, which is that cooking, household energy, and so on, including farm energy, is a part of a system. It depends on what's around you. It depends on your environment. So are you near a forest? Do you have access to solar resources and so on? But it's not just cooking also. People are very motivated to change when the possibility for income production, cash production comes in. And they're much less motivated to change when you just bring them a new cook stove. So again, this is what people are using. So wood, dung, you don't think of dung like that. That's what people do with it in Nepal. Charcoal, so not just biomass, but processed biomass of all kinds. And then I threw coal in there. I know it's not a biofuel, and I know we don't grow it. But if they're not using one of those, they're going to use that. And so there's this back and forth in the carbon cycle as well. This is some work we did in mapping, and so I'm going to start to hint at where we could use data. And so we sort of mapped the world. Urban areas you can hardly see in terms of land area. Of course, if we were to blow it up by population, it would look different. Electrified, not electrified, so we were using nightlight data to get at who had access to electricity, because it changes the kind, not only what they can use in terms of electricity, but the kinds of other energy that they can use. We were using electricity and nightlights also as a proxy for access. So if a place doesn't have easy road access, then the range of solutions, of course, is different again. And so this energy component of farm to table, first of all, is a huge time burden. It may or may not be a burden. So I can show you pictures like this that make people think, oh, those poor women. It's also an opportunity to leave the household, and so it's time that people may or may not wish to spend. But the one thing that is not arguable is that the use of solid fuels to provide household energy is one of the biggest killers in the world. This is disability-adjusted life years from the Global Burden of Disease Study. Household air pollution from solid fuels is number 4. And it's only behind the things that we in developed countries do to kill ourselves, like eat too much and drink alcohol and get all stressed out and have high blood pressure. So now I will hope to introduce some ideas about data. Who's got what energy resources where? And so we did this map. I can tell you, if you have several hours, all the things that are wrong with it, all the data we don't have, all the assumptions we had to make. There's more data out there than that. But the challenge is data access and acquisition, but also there's data at very different scales, time resolutions, qualities. People tend to take any data because there's so little as gospel, but sometimes it's just something scribbled on the back of an envelope that happens to make its way into a World Bank report. And then the institutional priorities on real data collection, like actually going out and doing the work instead of producing a nice glossy report. The priority is a problem as well, because people don't value that enough. Second, I like to think globally. What can we do all over the world? So if I can't scale it up, I'm not interested. But I don't have to scale it up immediately. So the global is the sum of locals. That means we have to do very well at understanding the local. And that means we need to evaluate not just change, but what people have tried to change and how people respond. So this is why I like social scientists to cause trouble, because we are getting to the point where we're making massive changes. There's an amazing urbanization, electrification, and so on. We should be understanding the responses to those things on a large scale so we know what potential there is for the future. Challenges. We have lots of remote sensing data. It is mostly full of artifacts. Ground truthing those data, believing what you've learned from them, and then instead of just providing a statistical description, linking those to causal forces. What's making that happen? Can we project it beyond what we've observed? Okay, last one. I do on-the-ground work, so we do measurements of emissions, and what's shown here is not our work, but that of somebody else, the different kinds of uses that are in a house. And what these were done from little temperature buttons that were taking real-time data on each device in a home. Well, that generates an awful lot of data, but sensors are getting small enough that we can begin to understand demand, and we can begin to understand how demand shifts in response to interventions. So the challenges there are management of large data sets and data interpretation, and then of course the right people to do that work are the people on the ground, not us, because it costs $4,000 to fly there, and et cetera, you know that. And so bringing up the capacity to generate the large data sets with quality. So that's it. I'm done.
So we're going to continue with our speakers and then have reserve questions and answers to the very end in the interest of time. Okay. Yeah, sure. Yeah. Okay, come on. Okay, let's move on to Paul Miller from Agrible.
Hello. Just got to get this ready, I guess. Okay, well, thank you for inviting me. I'm an industry person now, I guess. I have a startup that I've worked with for a number of years with a whole bunch of different founders. I have the pleasure of being able to work with my dearest friends that I met in graduate school long ago, and we've continued to build things and make what we consider to be amazing technology, and we hope our growers and users do too. And so happy to be here because I've had kind of an addiction to data science for many, many years. I'm an agricultural engineer by training, and we get to build kind of all this kind of technology specifically for growers to use. I'm actually the product line manager at Agrible, and there are a number of growers on my team. So I have scientists, I have growers, I have computer scientists, and it's a great kind of way to work together for agriculture. One of the things I wanted to bring up is it's my favorite day. So I literally do all of my taxes, no matter how completely complicated they keep getting with all of the K-1s and insanity that you've got to deal with the business. But what I love is I love TurboTax. I'm like addicted to this software. And one of the things that's strange about me is I've played in punk bands. I've did flyers, made hundreds of flyers over the years. I ran a record label, did all that stuff. And what's weird is that I use all of those skills to actually build interfaces for people. And I love this because you look at this and you see the most simplest kind of thing. It's just a recommender, like a recommendation system. I selected a couple of things. I donated to charity. I own a business, and you see all of these other inputs. And one of the things that's kind of funny about building technology for growers is that you actually need to fundamentally understand how somebody's going to use your science. And if they misuse it, weird things happen. And so you want to build products that bring them through, tell the story, and then kind of create something that they can use in their real lives every day. So one of the things I kind of been dealing with, since I would say 2006, is we built a product that gave rainfall to growers kind of on a lark. It was copied many times. Then we decided to do a business, because why not do the business instead of having people copy your technology? But one of the things that was interesting is that people, are addicted to checking their rain gauges when you're a grower, when you're anybody, gardener or anything. And what I've kind of come to discover is that when you estimate people's rainfalls and you kind of calculate just a simple variable such as this, that people are really hyper-focused on how accurate you are. And one of the things I tell people is that in a single 80-acre field, there are 89 million rain gauges, like in your garden. And when you say that, they're like, ooh, that has some meaning. And what we're trying to do is estimate kind of the average rainfall that falls on an actual agricultural field for calculation purposes. So you go from that kind of concept to kind of looking at pretty precipitation. So I have this thing that I call pretty picture syndrome. I'm not a fan of pretty picture syndrome. I stay away from it. But people love it, and it looks awesome. I was like, man, that's an awesome figure. But the fact is it does nothing. So you can't use it for anything. And it looks amazing, but when you look at it as a scientist, and what we've trained ourselves to do is to think of data, to look at what you're seeing, analyze it, understand it, and then kind of move forward. Most people don't do that. We're weirdos. So what we do in our first kind of inclination is to put that data into the hands of users, to see what they say, to kind of see what they'll do with it, and kind of what decisions they'll make. This is our Pocket Rain Gauge app. It's gotten over, I think we're at 1.5 million uses, and it keeps being used constantly. We built it 3 years ago to interface with our technology stack, and people are using it all over the country, and we're going to probably build one globally. So we have, this year for us is an expansion internationally to about 20 different countries, and we're going to keep moving from there. So just to describe who I am and how I think of things, this is one of our pitch deck slides. I work with a team of people. I can't build any of this stuff by myself, but with a team of people, you can do anything. Now, I wish the team was 3 times the size, because then I could build a lot more stuff. But the fact is, you go to war with the team you have, and you build the things that you can. So we have 50 people in our business. Myself and Chris, we've known each other for years. Chief Operating Officer Eric Snodgrass, I'm sure you guys know him on campus. He's an excellent meteorologist. And we have a whole bunch of other folks that are all part of building out all of this technology for people. And one of the things that I've come to realize over time is that you basically have to build a product for everybody. You can't build a product for a single use case in agriculture because a grower actually does every single one of these things every single day. So they're either marketing their crop, they're out planning, they're planting, they're growing, scouting, sensing, harvesting, planning next year, whatever they're doing. It requires a massive amount of logistics through the whole part of time, and you have to build tools for every part of that. When we used to build things, people would be like, well, what about spraying? Okay, well, we have to have a product that does spraying. Well, what about, logistics? Okay, we have to have a product for that. But the problem is that you have to be very focused and build those things correctly. So we have some core technologies here. Advanced weather analytics, crop growth modeling. We have fully autonomous drone tech that's got launched today. I'll show a little thing of it a little bit later. And what we do is we build systems that literally put it into people's hands and give them the insight to decide what they're going to do in the moment, whether it's sprayer guidance, hail prediction, mobile weather, market forecasting, real-time imagery, or seed recommendations, or any of those kind of other things. And here's some of that machine learning put to work. Here's a product called Field Story, and it's kind of the heart of our system. And in fact, we're working with a lot of researchers to help do some of their extension studies too. So we can get growers to put in data into the system. We have a strict privacy thing. We only work for growers. And we don't sell data to anybody else unless somebody's part of a program that we have already done with them. So we have a very kind of strict privacy law, kind of internal to Agrible. But this data goes into here, it goes into a format. The UX interface is easy as it can be. We process data internally. We bring in machine data when we can, make things as easy as possible. And what we do is we literally predict out the system rotations and other things. You've got 2015 corn, 2016 corn, and then soybeans for this year. And so we do analytics to predict what's going to happen months before people plan to do it based on their previous history. So we do those things so that they can really fundamentally have a system that works out of the box, but then actually works for them and that they can change and configure for themselves to make it even better. And they love that. So our users really get into this, and I think when you're involved with certain programs and other things, we have almost a 98% kind of usage rate of changing and making the system work for them internally. So one of the things that I'm really interested in and why I'm participating is that I'm really interested in input automation, synchronization, and correction. A lot of infrastructure things that I think we can learn from processing and analyzing this kind of machine level data, user data, and other things. Agriculture is a field of divergent technologies, stacks that don't make any sense, equipment that you think should work together, none of it does, business invoicing that is supposed to be translated into agronomic management. It's crazy. So we deal with a lot of that. Then also automated recommendations and conflict resolution. So it's a big part of our system currently, but we can always make that better. And what I would love to do with this process is I'd love for Morning Farm Report to just open and just say exactly what has to happen today. That's like a few years from now, but we'll be able to get there by doing some of these things. And then really driving and developing truly intelligent applications. Things that can guess that, what you're trying to do, how you're going to do it, what applications you should put down, why you might want to do something different. These kinds of things that people and humans kind of look at in deciding how they're going to manage their crops and then wonder about what you're asking them to do. You have to help through that path. You have to understand what's going on and develop systems that kind of really integrate with them on a field basis and an agronomic basis and a human basis, and that's what I'm going for. That's what Agrible's trying to do. So just to let you know, today is our launch day for our completely autonomous drone surveying program. it's, I don't know if you've used drones in the field. It's a nightmare. So usually we've built a complete aerial surveying system that's enterprise level. Data can be shared between anybody. It's like an insurance agency, crop adjusters, other people. Literally, you don't have to touch anything. It's completely wireless. It's completely cloud-based. And we built all of it here in Champaign. So we're very proud of it. We don't build the drone. Not yet. So, but we'll see. That's a different market for sure. But from the drone to the box to the field, you can do a survey. I don't even know how to fly drones. And like, I don't want to know how to fly drones because I hit a button. I program drones to do what I want them to do. And so that's what we're trying to do here. Make it the easiest way possible to use this stuff, and just excited about the abilities to use data in ag for growers, for users, and see what we can do with the technology as we go. So, thank you very much.
So our third speaker is Tom Evans from Indiana University.
Let's see, it's this one, I think. Okay, I'm kind of a pinch hitter here today, so I was disorganized enough that I didn't even put an introduction slide up. But my name is Tom Evans. I'm at Indiana University. I'm a geographer there. And my work has primarily been at the intersection of social and environmental systems. I started off my career doing remote sensing for the most part, and now I'm primarily working on the way that smallholder farmers in Africa are making decisions about the different kinds of environmental signals that they receive. And so I'm going to just focus on two dimensions here. Kathy invited me here. We're collaborators on some research in Zambia. I'm with Megan Konar here. And she asked me to talk about some international dimensions of machine learning applications. And so I'm going to talk about just two, because I think there are many, many, but in the interest of time, I'm just going to focus on these two dimensions here: remote sensing of land use and agricultural yield, and simulation modeling and machine learning. And so I'm getting a little long in the tooth, and I can actually remember the pre-Landsat TM days. Back in the early incarnations, 1972, when multispectral scanner was our remote sensing technology, even way back then, there was basically these two divisions between supervised classification and unsupervised classification. Lo and behold, here it is 2017, and that's now called machine learning. But basically, the same kind of image classification techniques way back in the day, and here's this little figure showing that supervised classification started when remote sensing came out, as opposed to the aerial orthographic imagery that was available pre-satellite images. And so there's been this long tradition of supervised classification in remote sensing applications, of course. And what's happened over time is there's been more and more progression towards higher resolution sensors, and with that has come the ability to detect objects in these land cover images, and then a transition to automated workflows and machine learning. So what does that look like? Well, so this is work from a colleague of ours he's at Princeton currently, but is moving to Clark University in a few days, basically leveraging high resolution images that are now widely available, and using crowdsourcing techniques to understand how to process this vast array of data into user identifiable and objects on the landscape. And so what it looks like in terms of the spatial footprint, much of this application is in, as my colleague in Zambia says, the great country of Africa. So it's taking a large sampling and taking these little snapshots of scenes that are now widely available. You can just grab them from publicly available data, and then use different processes to say, okay, within this little snapshot, within this little footprint, what is the land cover in these areas? And that was done traditionally back in the day using human experts. So there would be somebody who would take an image, or maybe you would have a GPS point that you would collect in the field, or you would have some imagery and basically draw a polygon around it. But there was a human that was behind that process of saying that, okay, yes, this is forest, this is savanna, this is Miamba woodland, this is maize, this is millet, and so on. And so you needed a human as part of that process. And that was then guiding the supervised classifier. Now, in terms of applications and thinking about the landscapes in these areas, I'm actually not a baseball fan, but I'm going to use another baseball reference. The slow-pitch softball version of this is, what is a center pivot irrigation system? Any monkey, and you really probably could actually train a monkey to look at a satellite image, and here's this little round circle, and here's a center pivot irrigation. Really easy. What's more difficult is, in terms of policy relevance, how do we discriminate rain-fed agricultural locations from irrigated agricultural systems? And in Africa, that's a big issue because the water availability and the transition of agricultural systems in these areas, one of the stories about trying to increase yields is water availability. So how do we translate this policy need into a data process that can be used given the prevalence of data that we have now and the techniques and algorithms that are available to process data? And so this is what it looks like if we discriminate these, and this is all about what I would call reducing the dimensionality of data. How do we take these remote sensing images and find something usable from them? So the panel C is the center pivot irrigation, the really low-hanging fruit. But what's more challenging is these areas down here, which are more general heterogeneous landscapes, and the goal is to try to identify an individual agricultural field. And the definition of what a field is very complicated because one farmer may have one field here and one field here. They may have multiple plots that are contiguous with each other, and they're doing very different management practices, planting different cultivars, planting on a different date, fertilizing them at different times, and that complexity basically is driving what we saw this morning about how these different types of phenotypes are resulting in different kinds of yields. Now, my mouth was kind of watering for the first hour because there was like, oh my God, the amount of data available on the environmental side is mind-boggling. And the challenge is to try to get to the same level of data on both the environmental side and the social side to understand things like adaptation to climate change, because we have this vast array of smallholder farmers in Africa that are trying to make very, very difficult decisions with very uncertain information, and they're making many, many different decisions. So how do we combine these things together? So one answer on the remote sensing side is that never have we ever had more data available to monitor the environmental landscape globally. And this is using data that is actually high resolution. So I don't know if you're familiar with Planet Labs, but there's basically a constellation of satellites now, more than 100 that are getting high temporal resolution data, 3 to 5 meter resolution, which is unbelievable. So that amount of data is vast, and there needs to be some automated process to make sense of it. And so one approach is these active learning approaches here. And so let me back up a couple slides and go back here. So what Lyndon Estes is doing is he's leveraging the abilities of Mechanical Turk. Amazon Mechanical Turk is basically this kind of micropayment system where you can say, okay, I've got this automated process, I need lots and lots of people to do it, and supervised classification is exactly that kind of thing. So he took all these samples of imagery, put them on the web, and said, okay, I want anybody out there on the web, look at this image, tell me what you think it is. Then he matched that for hundreds and hundreds of images and trained it and did actually intercoding interoperability and so on to produce great land cover maps using high-resolution images processed for this vast array of sites. And we're combining this with some social data as well. But the idea is that with Planet Labs and this wide array of remote sensing data, you can't use the traditional remote sensing methods to process all of it. And so Mechanical Turk is one mechanism by which to leverage machine learning to realize that vision. Now, I want to totally switch gears here and talk about the social side, because much of the work that I've been doing lately with Megan and Kathy is focused on this, the prevalence of drought, the spatial footprint of drought, and then seeing how farmers are responding in different areas. And so one method to simulate the way that farmers are responding to these different environmental signals is using something called agent-based modeling. And Many of you are probably familiar with agent-based modeling, but if you're not, you can just think of the way that a flock of birds behaves. And you may have seen these simulations where you've got this maybe 100 little graphical objects, and you've got one lead bird that's moving around the landscape, and all the other 99 birds are all looking at their little neighborhood and then following the flock as it moves along. Now, farmers are agents that perform similar kind of agent interactions. So if my crop fails, I may decide to work for somebody else who had a good yield that year. Or I may decide that somebody in my social network migrated to a city and moved off the farm, and that social network that I've got tells me, well, I might want to consider the same kind of decision. So we have all kinds of agent interactions that are driving the way that people are making decisions, and there are different ways of imposing that in a simulation model. So one simple way is using heuristic-based decisions. That means that if it rains on November 15th, then I'm going to put my seeds in the ground. Another way is using what's called utility maximization or satisficing behavior, which means that if my yield reaches 2,000 kgs per hectare, then that means that I've got enough money to pay for my school fees for my kids for this year. And another way is using decisions based on results from regression analyses. And so I can throw a bunch of independent variables into a regression equation and produce my agent-based model based on what I see in those patterns. But a new way of doing this agent-based modeling and matching our models to empirical data is using genetic algorithms and neural network approaches for parameter fitting and model calibration. And what that means basically is if I've got lots and lots of social data matched to lots and lots of social environmental data, then I can, and I hate this kind of pejorative term black box, but it is the right way to think about it, because instead of using these ways of simulating my agent interactions, which is based on my intellectual knowledge about what people are doing on the ground, I can maybe get a better fit with my models using these approaches, but I produce a better simulation at the expense of me understanding what's happening in the model. And that's an important trade-off. So this is some work from Steve Manson, who's another colleague of mine, who was actually doing this kind of genetic algorithm-based approaches in 2005, so more than a decade ago. So this is not really new necessarily. But what is new is that trying to scale up these agent interactions, and so Tami talked about the scale, and she wants to work at these global scales, but arguably we got to think about that individual farmer, because while we may be thinking about that flock behavior, the macro scale outcome, ultimately there's a lot of individual farmers who are very complex, have different situations on their fields, and are resulting in very complex decision pathways farmer to farmer. And the goal then is, how do we take these micro simulations, farmer-based simulations, where we can arguably get a better fit and understanding of what's happening on the ground, but we want that global scale. So how do we scale these agent-based model simulations up to a country level? And that's where the machine learning comes in, because we need high-performance computing to realize that vision. So we get this better parameter fitting here, but at the expense of maybe the understanding of our models. And yeah, we're trying to scale these up to larger spatial extents now. So what I would say in terms of wrapping up and trying to think about the comments or suggestions we were getting for the panel was to think about the following things. So is food security research more limited by computational gaps, that is the lack of algorithms, or by data gaps? And we saw some amazing data this morning. We know that there's a lot of algorithms out there that process data. I would argue there's an imbalance on the environmental data versus the social data, and that imbalance is a stronger imbalance when you talk about Africa versus the United States. But I think we really need to think carefully about whether we are limited computationally or in terms of data. And I'm a data person. I'm definitely not somebody who is shy about going to the field and collecting data. But there are absolutely physical limits to discriminate spectral signatures. I can do a satellite image, and I can look at an image of Zambia and say, yes, this is absolutely corn. No remote sensing image is ever going to tell me what cultivar of corn it was. And unless I have high temporal resolution data, I'm not going to get the date that that corn was put in the ground. And so that's where the social data comes in, and Kathy and Megan and I are doing some work where we're using mobile phone data and reporting with thousands of farmers in Zambia. They're telling us exactly the date that they stuck their seed in the ground. When we match that to remote sensing data on a field-by-field basis, that's when we realize the vision of matching the machine learning technology that we can get by processing lots of images with individual farmer kinds of decisions. Okay, so what I would say is that we're kind of dealing with a remote sensing fire hose. And when you've got that volume of data, you need machine learning. And what I hope is that at some point we can get to the same level where we've got so much social data, we also need to leverage the same kind of algorithms. But we'll always be without data we wished we had to understand why and how smallholders made different decisions. So what I would say is that let's not lose sight of this fundamental question, which is to strategically use machine learning approaches while understanding the limits to which machine learning can move research forward. That is the data gap and the computational gap. And I'll stop right there.
All right, we're keeping great on time. So our next speaker is Josh Peschel from Iowa State University.
Thanks so much. So I think in keeping with the baseball metaphors, what I'll say a little bit about why I think I'm here is that I've built a pretty decent career off of being what I would call a technology rover. Having the ability to work between very deep domains that are interested in data science and analytics, and in particular technologies. And so what I want to talk about today is some of my experiences with that. I think what the state of data science education is in both the collegiate and the practical communities, and I think some of the barriers and probably where we can have some improvements. So my current role now is assistant professor in agricultural and biosystems engineering at Iowa State University. And I would generally characterize what I do is helping people to use robots to better understand the environment around them. And we do this because we're mainly interested in the sensing and sense-making for agricultural, natural, and urban systems. We really, when we start talking about infrastructure in my research group, we talk about all of those systems being interconnected, and many, if not most, of the technologies that we've developed, we can use across all of them. And so what we might use for combined sewer overflow detection, we might be able to use for transportation, we might be able to use for cattle. And so I'm mainly interested in this area because of the cyber-physical systems that we can develop, the innovative technologies, and be able to ask and answer questions that we wouldn't have been able to if we didn't have these technologies. So a couple of the projects that I'd say best fit in the areas in which we're talking about today. So I'm the principal investigator for a City Digital UI Labs Smart Cities project in the city of Chicago. The mayor of Chicago has committed $50 million to the greening of the city, so bringing natural elements into the city of Chicago to reduce stormwater impacts, flooding, water quality, things like that. And we do a lot in the engineering community design these types of infrastructure features, but we often don't keep track of the health, and we certainly don't know in real time how well a street is living and performing. And so with mesh networks and a lot of the sensors that you've heard about today, we are streaming that information in, and we're giving it to a wide audience of people for the city, as well as the engineering design firms, to look at the health of that vegetation as it works to minimize the types of flooding that you might see in Chicago. It's important because, you know, Tami talked about scale. There's over 700 municipalities in the United States, 36 different states that have environmental conditions like this, and so would certainly benefit from this technology, not only in the United States, but also throughout the world. So that's one area. Another area, so I was a co-principal investigator with Steve Long and Carl Bernanke on an ARPA-E program that looked at mobile rapid phenotyping. So Pat talked earlier about the small little robot that could go out and look in the fields, and so we actually have built one of those, or when I was here at Illinois, I should mention. I was a professor here for about 4.5 years in the civil engineering department before I moved to Iowa State. And that little thing was great. The idea was building this low-cost piece of technology that could go out and get a lot of data. And let me tell you, That's a lot of information that came off that thing. As a matter of fact, I think we're still processing it from a growing season ago. So that's one area with the phenotyping. And then there's a new project that's coming online that we have going, and my collaborator colleague from Iowa State, Stephanie Hansen's here. And we're taking a lot of the similar technologies that you've seen today and applying it to beef cattle. So doing phenotyping and characterization for beef cattle as they are grown through the production process. And so what Pat showed, it's a little bit similar to that, where you can look at wilting processes. Let's say if we could look at cattle, which becomes a little bit different dimensional of a problem, but if you could tell, let's say, if an individual calf was getting sick about a day earlier, that's profound in terms of antibiotics and efficiency in feeding and things like that. So Stephanie and I were talking in the hall, and she had a really great app on her phone where she was able to say, well, this calf, over time, his feeding was going down, and you could see a little bit of correlation in the ear temperature, and that's that's really great information to have, and you get a little alert on your phone, and you could send to somebody out there to have a look at it, but we don't know why. So being able to deploy some of the similar technology like that Pat was talking about lets us really put a good track on why that may be happening, or at what point did that start, or how is that affecting other animals in the pen. So when we talk about big data and phenotyping, I want us to think broader than the plant science community. It's certainly being well developed, data science, machine learning, and plant science community for phenotyping, but I want us to think that there are many other areas in which this can be applied as well. So I think that where we are now, sort of speaking from an educator's perspective with regard to machine learning and data science, and those of you who remember back, I think where we are right now, would draw the comparison, saying that we're probably somewhere where we were with GIS back in the 90s. Except we have really much better pictures now, as we saw in one of the presentations. So we have a really good set of some baseline tools and software packages like MATLAB and R and different things like that that can give you access to those types of tools. And we've got some really great commercial grade tools. So I do a lot of work with Microsoft Research, and on the Cortana and the Azure platform, they've got some really great stuff. But you have to be very expert to get in there and do stuff with it. And if we think about the democratization of data science, putting it in the hands of everybody in the same way that we do with, let's say, statistics, I don't think we're there yet. And I think some of that comes in with educating people in college, but certainly continuing professional development. And really, if you look at the disciplines like plant science or animal science or civil engineering, environmental engineering, and you've got these silos, but what I think we lack is the time in the field with the data science that they would become connected. So there's awesome things that are happening in plant science, awesome things that are happening in animal science, but there really aren't the horizontal bridges to connect them. And I'll come back to, I think, why that is. So we've got this really great graph with some gaps. I think that's one of the things that we can change. I think in terms of the leading edge, one of the areas in which we're working is we have all this data. How do you turn the data into a self-learning entity? So we often talk about metadata, and someone has to put that information in there. Many times it doesn't happen. So how do you leverage accessibility, results that have come from those data sets that carry along with the data itself, such that it may inform a new user of something interesting that might exist in their particular domain. So I think self-learning data is really a leading edge thing. And one of the areas where we work, I think that is another leading edge thing is turning what we call little data deserts into big data rainforests. So my PhD students here are young, who sit in the back, and we spent some time in India a year or so ago. We're funded by NSF. We're really happy to be able to go over there and try to figure out why farmers' agricultural tanks were drying. And it was a little data problem that didn't have really anything about that. And we were able to take our robots over there and capture more data than you would know what to do with. And we were able to ascertain that farmers were using microdiversions, check dams, things like that. There was a small but subtle transition in the land cover from traditional cash crops, or traditional crops into cash crops. specifically eucalyptus, which was requiring more water. And so for the first time, we were able to know in this area where nobody had any information how much the hydrologic opportunity cost was to these diversions, such that the tanks weren't filling, farmers were having to drill groundwater wells. And if you look at the failure rates of that, about 1 out of every 5 years, they were losing one of those wells. Well, one of those wells costs about 1 year of income. And if we just think about that in our terms, I mean, how bad would it be if you lost a whole year of salary just to do your job? So I think being able to put technology like this, data science and such, in the hands of citizen scientists in different parts of the world and economies of scale is very valuable. And so turning little data deserts into big data rainforests is important. So I think the barriers that come into play are really in the education, and I've seen this in a couple of different ways. I've given talks at Microsoft where we go in and talk about flooding, and usually by the end of the talk, you have people come up and they're like, this hydrology stuff is really great, right? How do we learn more about this? There's infiltration? This is awesome. How do we learn this? So I think having more 101 style classes for folks that are in the computer science community would be helpful. Bringing that domain expertise, but then also bringing it to the people who are students or employees in the communities in which we work. So having a greater integrative educational experience, I think the interoperability of the data and the tools are going to be important, that you don't silo the tools and the data. I think that's important. And I think one of the things that I guess I'll take a little bit of a cautious approach, because I've been doing this for a while and I've looked at what's happened with GIS. Back in the day, that was you know, you had your own, and universities still have classes, but that was a big thing. You were doing research in GIS. In a lot of ways, GIS has transitioned into certificate programs, and it's become prevalent in the community college system, and that's fine. But when we start talking about turning on all these data science programs and things like that, do we run the risk of doing what has happened with journalism schools, where you have people who are highly trained in algorithms and programming, and they perhaps might lack the domain expertise? So you have people who can write really well in the mechanics of it, but they've not really had an experience about what they are supposed to be writing about at a deep enough level that it is meaningful in terms of the results. And I don't care if it's politics or economics or data science or chemistry or what have you. Having people well grounded in the domains, but that can also speak this language. And I think we've seen this evolve a little bit with GIS in terms of people having that particular skill set. And so I would hope to see that with data science, and I hope that it doesn't go in that direction where it becomes a little bit pushed to the side, or we develop people who are very good at the mechanics, but they aren't as good at producing meaningful results. So those are the big highlights for me. Happy to answer any questions after, and with that, I'll yield the rest of my time. Thanks so much.
Our last speaker in the panel is Lakshmi Kumar Matukumalli from NIFA USDA.
So again, looks like the only founder amongst the group here. So I'm Lakshmi Matukumalli from USDA and NIFA. It's the extramural. Oh, sorry.
You might want to just take the guy. Yeah, thank you.
So I'm from USDA and NIFA. It's an extramural funding agency that gives out the grant. So my background is in bioinformatics, and also my PhD research was on machine learning. So I was working with soybeans, trying to identify, the paralogs within the soybean. So there's a problem there. And also, at the time we were doing the SNP discovery. So when we find a SNP, so whether it's a paralog or like it's a SNP, so that was the distinction trying to make with that. And that the SNPs that were developed were used for developing some of the initial SNP chips for the soybean. So I transitioned into the cattle, so did the part of the cattle genome sequencing project, and also did the bioinformatics for the developing the 50K SNP chip in the cattle. So, and then I was part of the team that implemented the genome selection. So the genome selection, the quantitative genomics, it's not called the machine learning, but in theory it is like you're training the data with the known phenotypes and to get the genome predictions, and then you're using it for the unknown. So that's also a machine learning. So that's kind of a brief background. So I joined NIFA about 5 years ago. Since then, I've been working on funding some of the great genomics related projects. So that's the kind of my background, but also thinking about what we do as an institute. We have a broad variety of the projects that we fund, going from genetics, genomics to organic agriculture, beginning farmers, and a lot of the social programs, the family consumer science programs. So we have a very broad variety of the different data sets that we generate, and we can't have one solution that fits all. I think probably some of the sciences like the genetics and genomics, they have a very good infrastructure, and also the way that you put in the data into public databases, and so there is an infrastructure that was there, but it's kind of the things that are currently lacking in the other fields of science where the NIFA funds. So we have been thinking about it for the past few years, and so that's where I think the big emphasis for us is. So again, with that, so again, the data is everywhere. So going from the robotics, the genome sequencing, the landscape modeling, some of the personal devices, and the use of the drones. And a lot of data that was collected, as Pat has mentioned, is in the form of the the spreadsheet. So again, how do you get that kind of data to being able to get into a digital format? So that's a big challenge that NIFA is trying to address. So again, looking at the definitions of data and cyber infrastructure, a few examples here, talking about what this means. But again, as I said, we are very early in the stage of trying to discover what it means as a big institute, for all the different data that we are generating. So, one of the first steps in the process is last year in October, along with the Midwest Data Hub meeting, we conducted the first initiative we call as the Food and Agriculture Cyber Informatics and Tools initiative, and we used a data-driven tool that's called the Co-Digital, and solicited input from the community on various different topics. So that's the topics that were given are in the bullet points here. So as to asking the community to say, what are the different things that we need to be doing in the area of the data science. And we got some good input. And some of those things are listed here, so that we received the input from the community. And I think it's kind of probably for the audience here. So this is some things that you can probably expect what the community wanted to see, like the data infrastructure and management, creation, collection, provenance, and characteristics of data, like developing data standards, developing repositories, thinking about the privacy, when we have, players like Microsoft, Amazon, how do we work with those, the big data players in the form of the cloud computing, and we have other federal agencies that are also working in this area, so how do we partner with them? So those are some of the type of the questions that we have had in this, as received as the input that we should be thinking about. So again, in the space, the data space that we think about, like, how do we look at the NIFA's role is to, coordinate and enable agricultural communities to effectively use the data, improve resource management, integrate new technologies and approaches, and again, looking at the value of the data for all the farmers and agricultural and food industries, and gain understanding of the data and how it impacts the value chain and those kind of, and how do we increase the competitiveness of the U.S. agriculture. So again, these are some of the broad goals that we look at. And in terms of how it will be enabled is some of the questions like scalable data infrastructure management systems, using the FAIR principles. Again, like, we have a lot of data sitting in, PI's hard disks, or like, so those kind of, like, you have some of the data sets that require the people to publish the data, but where, those standards are loosely implemented in other programs. So we are trying to develop the protocols and also data management plans along with the proposals in all programs. So that's, kind of things that we are asking them to do, and also, looking at the analysis, the technologies, and the application side. So developing, say, for example, decision support tools that, one of our speakers mentioned. How do we get the students, professionals trained in the area? What's the visualization tools, and again, the computer systems that are required for those, enabling those. Again, some of the going forward, the way we look at it is, again, as I said, like, we have different programs. So each individual program, the data needs are very different. Say, for example, the plant science versus animal science, or food safety, or social sciences. So we have, what are the requirements for each of those in terms of data, each of those communities. So, we have to look at it from the tailor-made thing. So what we are working on mostly is been a very heavy emphasis on interagency programs. So a few examples are, we participated in a collaboration with NSF in the food, energy, water system. So where we offered some joint programs to facilitate a large data analysis, large-scale data analysis modeling, and one of the thing was the foundational part is developing some workshops, looking at the questions, what the community needs, and then looking for the solutions as a next step. So another example is we did a joint partnership NSF in high throughput phenomics. So it is both covering the plants and animals. So that's another program. And a couple of years we offered programs that in the food security to develop high throughput phenotyping in the area of the, again, plant and animal phenomics. Pat got one of the grant last year in that. So along the lines, this year we're offering a joint, not a joint program, but a joint between two of the programs that we used to offer. So one in the challenge areas. One is we used to offer a water and a food security in a different program. So this year what we're doing is combining those two and asking a question about water and food security. So again, like, we are looking for some of this, the communities here to look at the big data issues. So like when you look at the water problem, so it is not a regional problem, it's a national problem, and you need to do a lot of data crunching to be able to connect those two and be able to come up with some good solutions as to develop sustainability of the food production system. So that's the kind of thing that we are looking at. And another area that also we are looking at is in terms of the functional and annotation. So we talked about, like, how do we developing prediction equations, like looking at it from a black box perspective and going into the functional genomics, where you go into the science and find out what's the genes are responsible for individual traits. So that's the and the training needs and so forth. So, but one of the requests that we are asking from the community is to help us do some workshops and around the area of the food and agriculture, and come up with some white papers, so that, like, for each of the areas, so how do the NIFA needs to strategize in terms of better use of the big data problem. So we are asking the community input in that, and then those white papers will help us redesign our programs so that they're better suited to work with the big data and be able to use the cyber infrastructure tools for shaping our programs. So with that, I'll be happy to take any questions.
Okay, so we've got some time for questions. Let me just maybe start off a little bit and set the stage for the discussion. So, all of you presented a number of different diverse applications for big data and machine learning. And one of the things that seems to come across is that there's a lot of unevenness in the availability of data. So there's lots of data available on many of the biophysicals and things, remote sensing data. There's not as much information perhaps on some of the ways that data then impacts the outcomes that we're actually interested in, particularly if we look at, of course, on the behavioral side, it's probably the least available. So, there's obviously big data gaps. And how do you see, given where we are with the data, what do you see as the ways that we might be actually able to get more data on other aspects that we need, maybe, hydrology or the energy consumption and its implications for health, and in the absence of that data, how useful is it to then proceed with detailed data on some aspects and not enough data on other aspects? So, maybe we'd like to tackle that.
I'll start here. I just wanted to bring up one of the things that I think is interesting about some of the data access that Agrible has is we not only have our user data, so we know like management and other kinds of details, and the system is configured to use that data accurately and correctly, but we also work with a lot of agricultural retailers. We work with a lot of agricultural companies, and then consumer goods products and other things. And as part of these processes and as part of these programs, we actually get more growers into our system, in addition to accessing data that just would not be available in any other way. And I think that's really interesting and intriguing. And I think there are more partnerships that can be made between industry and academia too, in that way too, especially if we preserve anonymity and other kinds of privacy in the data stream. So,
but maybe just to follow up a little bit, the case of like agriculture, so you've got, you're getting a lot of information about how farmers are, what they're applying, how much nitrogen, you get a lot of information on weather, soil, and all of that. But there's still a lot of information lacking on exactly how nitrogen affects yields. So that's because that's such a dynamic fact, and knowing how much nitrogen is in the soil and going from that and how much is available for plants and how it'll affect yield. There's still a need for a lot of agronomic, research on that. So how do you kind of overcome that gap?
Well, there's no question that there's a role for pure basic research. I mean, as a company, we can't do pure agronomic research unless we're like incredibly huge, right? Like we have to be focused where we, have burn rates and things like that. We have to get products out the door. We have to do those things. But there's a lot of actual known science that's not even gotten to the growers. And I'm glad you bring up nitrogen, because we have one of our products is a nutrient engine. We call it the Advanced Nutrient Engine. Literally, when we launched it, growers were amazed that that they saw the mineralization rates that were possible in their soils. So that literally led to less applications of nitrogen fertilizer. And we have testimonial work where people put down like 25% to 50% less fertilizer and yield their highest yields last year. And so, you know, we actually made a change in that usage, the energy usage and all that by doing that with just whatever is available now. You know, can it be better? Of course. You know, like we actually collect all of the genetic, like actual seeds that people plant. They want to plant their exact seed in the system. We have that data. We can work with people, and we can see what some of those things react with when they put their yields into the system and other things too. So.
All right. Technology is not going to work if I can't turn on a microphone. So let's see, a couple of things come to mind. First of all, there's always going to be a need for ground truthing in some manner, and that notion comes from the remote sensing community, of course, but it could be in models or agent-based modeling or responses or whatever. There's going to be a need for ground truthing. And the scales at which we're trying to work and project are very large and contain a lot of diversity. And that means we need a lot of ground truthing. So the fundamental thing that we have to get over is that the first time you do it, you can publish it. The fifth time you do it, nobody cares. And this is a structural problem with what we are doing in terms of data science and global knowledge. And so I'm not really sure how to get over it. I think extension people have some good models. I think possibly working with NGOs who do not have to have a knowledge product can potentially be a good model. But we need to think about outreach, not just as outreach like we're doing you a favor, but outreach like we are putting the knowledge gathering somewhere else, and we're partners in that. And then I'm glad you brought up privacy, because that's huge when it comes to behavioral stuff. Gosh, I don't want to tell anybody why I did something. I don't know about the rest of you, but that's personal, right? And so how can we get enough information to be predictive without sort of horning into people's lives? I'm not exactly sure about how to do that either. I think one of the ways, and one of the things we need to be thinking about is mutual benefit. What we're doing needs to benefit other people immediately, not after 10 years when we publish it and then they, you know, inherit it from the news. And that can be a little bit of a trade-off. Tell me something about you and I'll give you feedback that, that benefits you. But I think we need to be really more careful about some of those things.
Yeah, I really briefly alluded to this methodology we've implemented in Zambia and Kenya of getting weekly data from thousands of farmers using SMS messages. And that's been one method to harmonize the temporal resolution of environmental data and social data, because we have environmental sensors in the ground that are getting, well, really 5-minute data, but it's being aggregated up to this horrible time step of 1 hour data. The 1 week data is still groundbreaking, because the traditional state-of-the-art in agricultural monitoring in Africa is basically annual data at best. That's if there's funding available for that country to do a crop forecast survey that year. So what we've been able to do with our mobile phone program is, for about the cost of $0.25 per farmer per week, we get about 6 data points for thousands of farmers. And I wouldn't, there was a great workshop here last year on big data, and I wouldn't call that big data necessarily, but it allows us to do things temporally in terms of matching the frequency of the environmental data with the farmer decisions. And I'm glad you addressed the point of confidentiality. That's really important. The other side is data quality, because just as the citizen science kind of development changed the way that data was being used by researchers, I think we also need to be careful about these mobile phone applications and the way that mobile phones are being used. But there's basically two approaches. One is this in-depth approach where you give a farmer an Android phone and you create a survey on that phone and you put 300 questions on it. And then you can do that for some small number of farmers because you can't give everybody in Africa a phone, for example. But all these farmers have these non-feature phones that cost about $20. And with that, and you use SMS, you can get a ton of data from these farmers. The biggest cost then is the cost of actually getting on the ground and getting, for example, an ag extension agent to enroll a farmer in the program. So it becomes a human engineering problem as much as a computational or data problem. But I think that there's going to be increasing awareness as this is being used more. We're now in our third year of data collection, and we've been extremely careful about this issue. When we talk to the farmers and we enroll them, they say, we want you to tell us what cultivar to plant. And I really, really don't want to do that because unless I go and get a soil sample from that farmer's field, I don't want to tell them to plant cultivar A, B, or C. But what we can do is aggregate data, and if we get, say, 100 farmers in their local area, and they can see what the distribution of planting dates was, and the cultivar is being planted, then we can deliver something usable back to them. And we're not giving them a recommendation, but we're helping them see insights and stories that they might want to adopt in the future. So I think that's the pathway that things are going, but I think it's really important for this to be a sustainable program where it's not just the researchers that are doing this, but it's being implemented in partnership for a long-term solution that hopefully the countries themselves are implementing.
Could I ask a very brief follow-up? How do you convince the farmers to send you an SMS multiple times per week? What is in it for them?
So we'd give them this quarter, this 25 cents.
That's for them, not to pay the SMS charge.
Well, we're a little bit, we tell them how much we're going to send them. The actual cost that they incur on their phone is below that 25 cents. And so it depends on how many questions they actually answer, but they're definitely not going into debt by participating in our program. Sure. But we're also saying when we're on the ground, we say we are researchers, we're not a development project, we will be coming back and we will be summarizing this information. And so there's the individual benefit, but then also this idea of the report that we're generating for the communities. But that takes a lot of resources to get back to the people.
So I wanted to kind of address what you asked about how do we effectively put together these clearinghouses to look where the data gaps are. And if we look at what's been done well in the past, I don't think any hydrologist in here would argue that USGS and the DEMs and NASA and the land cover data sets and EPA and some data sets have been incredibly valuable to a lot of the work that's been done. And I think if we look at the critical zone observatories that have been put forward all across the country through National Science Foundation, bringing that data forward, having it quality controlled and making it available to many different types of people who are doing science, regardless of what it is they're doing, has been incredibly valuable. But there's it's kind of a new day when we talk about clearinghouses and such. I don't know that I count so much on EPA putting forward a new database of things. And so I think what we found in our work in Chicago is it's absolutely necessary to go forward with public-private partnerships, to have a Microsoft or an Accenture or City of Chicago and academics putting together these databases that are valuable for people. But can you guess the number one thing that we argued over more than any other thing in the process of actually doing something like this? Who actually owns the data? So we're doing all this stuff, and I get the private sector angle. I mean, I have a startup company, and we like to collect data and help people out and make decisions and things like that. But we talk a lot about the tools and the technology, and we think of software as the commodity, but in reality, it's the data that in itself is becoming the commodity. And we talk about that in civil engineering. The information about the building at any site X is generally becoming more valuable than the brick and mortar itself over the lifetime of the building, knowing how to manage it, with regard to energy and water and all of that type of stuff. So the barrier to doing the clearinghouse and to understand where the gaps are is really recognizing that the data is going to be the commodity, and then how do you deal with that in terms of making it accessible to people and that type of thing. So it's a clearinghouse, but it's probably of a different variety than we've ever seen in the past. And so it's just something to keep in mind.
Can we open it up to questions? Yeah, sorry, go ahead.
Just to follow up on that is having the trust between the public-private partnership. So just the dairy example, when the genome selection and the methodology that came out, so there was an existing public-private partnership as to how the phenotypes are collected by the facility at the USDA ARS, and then they have the semen repository and all the phenotype data, so that helped them very quickly implement these new programs and benefit from the whole genetic improvement. So I think that having that kind of a trust between the different partners and players is very important. So, but that kind of trust is lacking in, when you come to poultry or swine. So that's those are controlled by individual companies, and then working with them to develop the trust has been an issue. But there are examples there, even in the swine, for example, when they had the problem of the porcine reproductive syndrome. So, but all the companies came together, the US and Canada, the funding agencies partnered, and so they were able to develop a consortium to work together on this problem jointly. And so they have been very good, highly successful in terms of leveraging the funding and to successfully address the issue. So I think the developing those partnerships is very important, and the community can play a big role in the process, and as well as the funding agencies.
No, that's an important point. So I mean, we've got the situation where we've got private companies like Agrible and others that are accessing huge amounts of farmer-specific information that's not available in the public domain. And we've got researchers who are going out and doing it and are limited in their ability to do that because of the issue about how much will the farmers provide, and how much can you as a researcher fund. And so at some point, I guess there'll be a demand for, as more and more competition, and you can, address this, Paul, I'm not sure, but as more and more companies like yours come up and are pitching their products to these farmers, and farmers have to select between Agrible and Climate Corps and so on, what is the external validity for how much better they might be with you versus others, and is there a role that researchers can play in that and be able to work with the data with confidentiality and try to provide some third-party validation for the work that, the algorithms and the outcomes that you're getting. And the role that USDA can play, perhaps, in trying to manage confidentiality. So the USDA, of course, you have the ALMS data. They collect this data. It's an annual census of farmers that is being housed at NAS. It's the Agricultural Resource Management Survey that's done, and grower confidentiality is being protected, and yet that data is made available to researchers, stripped of identification, and that can be used, and it's very informative. There's just tons and tons of research that's come out of it. So do you see a role for that kind of providing that kind of access to data, and or you and other companies, and try to build these public-private partnerships to do that?
Yeah, there's a lot of topics there, and one of the things about our company is that we fundamentally believe that the growers own their data. So, like, there's no question to that in our eyes, and we use their data to help them, and we use their data to create communities where they help they can get them their help themselves. And what's interesting is that when you deal with privacy and you deal with these things, a lot of the growers in our system, they're very private people. We understand that, but when they see their data aggregated to help them and see what their community is doing around them, they're very excited to see that. There's a totally different change in how they view the data and how they function with it. Because when I say, well, we'll make it anonymous. So when you make that data anonymous, it sounds scary to people, right? I can't even say the word. So the fact is, though, but when they see that in use and they see it in their operations and they see these kind of, we have a product right now that we're working with a retailer. We process the data for everybody in the retailer's program, and they see it all there, and they're like, wow, that's awesome. You know, I'm either doing better, and if they're doing not as well as their neighbor, then they are interested in why. They'll call the retailer and ask them what they can do better. So that's a great use of that product. That's all industrial kind of like relationships and things. But you know, we also have programs where we're working with extensionists that want to collect their data. Morning Farm Report, our flagship platform, is a great way to enter data. It's built to enter data in accurately and fast. And so, you know, they want to do that. And we'll work with the researchers, anybody who kind of, like, we deal with the terms of service. We put the platform up there, terms of service for it, and then they know their data is going to be, you know, made anonymous and processed as part of that platform. And I think that's great. I think when you start getting into more and more tenuous benefits to the grower themselves, that's when they're like, why should I do this? And we work in partnership with the growers to actually compensate them through our various programs with different retailers to do that. So we feel like because we are working in partnership with them, and we can do that and navigate that process with them and do all the legal stuff that's required for it, we can make those things happen. But can you dump all of their data into some database anybody can get access to? We're a ways from that. And I think that we have to ask ourselves why we'd want to do something like that. There's a reason why, like, rates of, you know, surveys and things are going down too, because people know that there's value in their data. They don't want to contribute it without getting that value back. So.
This might be a question more for John. So you had success being a unicorn term technology rover throughout your career, and I'm wondering if you think this is something that might help some of the gaps in the data that we're seeing, and why more people in academics aren't doing this technology roving.
So see, you were listening. I left that part out when I said I was going to tell everybody, why aren't people doing this? So one of the great challenges of working in this space is that you're very much an interdisciplinary person, and a lot of the enterprises in which people work aren't well suited to evaluate the interdisciplinary nature of what someone might be doing. So I'm going to pick on Megan Konar because she's not paying attention, but no, I'm just kidding. No, Megan and I are old friends and colleagues. So Megan, for example, works on looking at applying graph theory to food water problems. So in part, Megan looks a lot like a computer scientist. In other ways, she looks like a natural resource person. She's in the civil engineering department. And so, you know, she's taking the initiative to do a lot of this cross-cutting stuff. I mean, myself too, and I know other people who are working in this space. But there isn't an assistant professor that I haven't talked to across the United States who is fully comfortable thinking that they're going to be evaluated for promotion and tenure by senior people who may not well fully understand what it is that we do. And so being, you know, because I can think of maybe one, maybe two senior people in the country who do similar things in the way in which a lot of early career faculty are doing them. And so I think that sometimes there's a little bit of a discouragement because the work looks a little production versus fundamental in terms of its contributions. But I think that what I see is that people are taking the jump anyway. I think if there were better ways in which enterprises, particularly the academic community, were able to evaluate that type of work, or there was more confidence, then I think more people would be doing it. In business, it's very different, because if you got a skill set, let's go make some money, right? It's not quite the same thing. But I think in the academic community, there is a transition towards feeling more comfortable to be able to work in this space that's going to speak to filling those gaps, doing more of the interdisciplinary data science work and things like that. So I think just giving it a little time, and the more people who choose to work in those spaces, I think that's going to fill it out a little bit more, and the community will benefit, and there'll be more people working in those spaces. So it's a good question.
Just sort of an observation about data and data privacy and its value. I think that at times there's a sense that, of course, farmers would share their information when there's not necessarily a recognition, oh, this is a $5 million or a $10 million enterprise. In what other sectors of the economy would we expect someone running a $5 million or $10 million enterprise to be so forthcoming with the internals of their operations? No place else. And so I think that's part of what we need to remember, that farms, at least in the United States, are businesses. And that's an important aspect.
So as I talk to farmers in Iowa, corn farmers, they're worried that as these predictive models get better and better, they're going to put themselves out of a job. So they bring capital and they bring decades of experience in how to grow corn. If the models get good enough, large investment firms can buy the land, hire tractor drivers, and eventually get rid of those because they'll have autonomous tractors. And we know that whenever innovation doesn't play fair, the benefits, clearly there will be benefits to society, but there are going to be losers, winners and losers, and it's the losers I'm talking about. What, if anything, are your ideas about how to protect farmers, or at least, how to protect farmers from this?
I don't know if you want to. Can you just talk? Yeah. Well, I guess automation and all of these things is something that's critical, and it's something that we have to deal with over the long term. I mean, farms already are growing in size every year. The fact is that you look at the price of commodities, you have to optimize your business, you have to follow economies of scale problems, and there are going to be people who are going to do these things as best they can. The example I gave before of one of our growers literally cutting their rate of application meant they could spend that on fungicide. And last year was a pretty disease crazy year, and they got a huge benefit from the fact that they did both of those activities, and they were really only done one of those activities if they had to put down nitrogen. I think that as a company, as an agricultural company, we want to work with growers. We work with the whole process. There are a number of other people and companies that are, whether you like them or not, they're monopolistic, right? Some of our competitors are. They have a vested interest in predicting analytics that showcase their yields are better than other yields. It's why our growers don't trust any of the trials that are out there by companies. And what I'm getting at is that there is a place for us to work with growers to help them optimize their operations, to deal with the financials, the marketing parts of things, looking at these data and interpreting that, and letting them kind of kick the tires and try to integrate those things into their operation to be the best they can do with what they're trying to do. along that way, there's an entire industry that's out there too, and there are people who are also trying to probably, turn it into the Amazon of agriculture, and there are people whose livelihoods are part of that process too. And Agrible, as a company, respects all of those people, and we want to work in the agricultural industry as it is. And as anything transitions, we'll help to figure out how to transition that process. That's at least my philosophy, and I think our company's philosophy.
Yeah, I think diversification it could be one of the solutions. So we have, whenever you have one single crop like dominating, and so then, you have to sell that crop, or like even sometimes even that marketing itself becomes an issue. So I think having that diversification about like what are the needs and growing the different crops, so those kind of things where you'll constantly need a human expertise to be, manage all that stuff. I think, yeah, that.
All right, I think we'll bring it to a close. You want to have the last word, Tami? No.
I was going to say your question, I don't have an answer, but I think your question is bigger than that. I think what we're all proposing is using data to optimize, and we're using data to optimize because humans haven't gone that extra step, and we're going to have to face the fact that if we think data and machines are better at optimization than humans, we're going to have to find a way for humans to retain their dignity. Philosophy.
So on that note, please join me in thanking our panelists.
So that brings our morning program to a close. Thank you all for coming. We thank the sponsors who have supported this workshop this morning. We're going to break out into work session this afternoon. For those of you that were only here for the morning, we hope you'll be able to come back tomorrow. Thanks.